In this video, we're first going to revisit indeterminate forms of limits, where, for instance, we get infinity divided by infinity, which doesn't result in a limit. And then we're going to look at L'Hopital's rule, which is another strategy we can use when our initial attempt at a limit gives us an indeterminate form. Recall that indeterminate forms include values like 0 divided by 0, infinity divided by infinity, or even infinity minus infinity, and so forth. If you end up with any of those, up to this point we have had a couple of strategies that we could use to deal with that. Again, first of all, if I were to try to direct substitute 1 into this function, I would end up with 0 over 0. So now I know I can't just direct substitute. But what I can do is I can use the dividing out technique, where I'm basically am factoring, if it's possible, of course, factoring out a common factor, or dividing out a common factor. So in this case, my numerator can turn into 2, and then that leaves me with x squared minus 1, which was x plus 1, x minus 1, and that reduced with the denominator. So now I'm really just taking the limit as x approaches 1 of 2 times x plus 1. So that's 2 times 1 plus 1, which is 2 times 2, which is 4. So that is the limit. So the limit of this function is the same as the limit of this function. Now let's look at the second example. In our second example, obviously, if I were to plug in infinity, that would give me infinity divided by infinity, which is indeterminate. So instead, we used the greatest power of x squared, and we said, let's take the limit as x approaches infinity, but take every term divided by x squared. And that gave me 2x squared divided by x squared plus 1 divided by x squared. So really I'm taking the limit as x approaches infinity of 3 minus 1 over x squared divided by 2 plus 1 over x squared. Now we know what's going to happen here. As I approach infinity, 1 divided by x squared and 1 divided by x squared are both going to approach 0. So now I just have the limit as x approaches infinity of 3 divided by 2, which is just 3 halves. So if I take the limit, I shouldn't have rewritten limit on that one. These are going to turn into zeros, and that just leaves me with 3 halves. So again, up to this point, that was really the essence of our strategy, is if we can divide anything out, we should, and if we can divide by the greatest degree of x, we should. In dealing with transcendental functions, we can use those same strategies. So for instance, in my first question, I can see that if I did direct substitution, this clearly would give me 1 minus 1, which is 0 in the denominator, and that would give me 1 minus 1, which is 0 in the numerator. So instead, I can use the dividing out technique and say that this is just a difference of squares pattern. So the square root of e to the 2x is e to the x, so e to the x plus 1, e to the x minus 1, in my denominator, e to the x minus 1, and those cancel. So now I just have the limit as x approaches 0 of e to the x plus 1, which is e to the 0 plus 1, which is 1 plus 1, or 2. So pretty straightforward application. Now for my second question, I can't just divide everything by x because that's not going to help me. So I still have an indeterminate form of 0 divided by 0. If I tried to divide everything by x, it wouldn't help because it's not going to get rid of any of the values of x. If I tried what I did up here, which was to factor it, it's not going to help because I don't have anything in the denominator to help me. So I could try writing this as e to the 2x divided by x minus 1 divided by x. But again, now that just leaves me with infinity minus infinity. So now what? Well, now I'm going to have to use some other strategy. But before we go on to that other strategy, let's just remind ourselves that other ways where we were trying to find the limit of a function before we really knew how to find the limit is we could use a table of values, which I'm not going to do for this particular question, or we could graph the function. So what you can see to the right is a graph of this function, and we're looking at the limit as x approaches 0. So as x approaches 0, it appears that the limit is 2. Now there's a hole there, and that's okay. We knew there was going to be a hole there because if I plug in 0, it's not going to work, right? But it appears that the limit is 2. The question is, how are we going to mathematically find that without having to make a table of values or graph the function? L'Hopital's rule to the rescue. So L'Hopital's rule is a great way, using calculus, to be able to determine the limit of a function. And the conditions that must be met is that f and g must both be differentiable functions, and that the derivative of g of x cannot be 0, and that is because g is the function in the denominator, and when we take the derivative, we need the derivative not to be 0. The way that we can find the limit of the quotient is to find the limit of the quotient of the derivatives. So essentially we're saying take the derivative of the numerator and the derivative of the denominator, and that limit is going to be equivalent to the limit of the original function. So let's take a look at this. Now keep in mind we've already discovered based on the graph that we should get a value of 2 for the limit. But let's take a look at L'Hopital's rule. L'Hopital's rule says we're going to take the limit as x approaches 0 of the derivative of e to the 2x minus 1 and the derivative of x. So what's the derivative of e to the 2x minus 1? Well, the derivative of e to the 2x is, hold on, let me rewrite this so I don't forget. The derivative of e to the 2x is e to the 2x times the derivative of 2x, which is 2, and then the derivative of minus 1 is 0, so I don't have to write that, and the derivative of x is 1. So really I have 2e to the 2x divided by 1. Well, now all I have to do is plug in 0. So 2 times e to the 2 times 0, well, e to the 0 is 1, so 2 times 1 is 2. And that is the same limit that we got when we looked at the graph of the function. Let's take a look at these 3 practice questions, and we'll just utilize L'Hopital as needed. So for the first question, if I were try to do direct substitution, I'd end up with infinity divided by infinity, which doesn't work, so that's indeterminate, and I need to utilize L'Hopital's rule. So let's take the limit as x approaches infinity of the derivative of the natural log of x and the derivative of x. So that's the limit as x approaches infinity of 1 divided by x divided by 1, so 1 divided by x. And what do I get when I take the limit as x approaches infinity of 1 over x? I get 0. So the limit is 0. For my second question, again, first thing I would do in this particular question is to rewrite it so that it was a fraction, because this is x to the 1/2 and this is over e to the x. And again, if I were to try to plug in infinity direct substitution, it's not going to give me a solution. So instead, let's use L'Hopital's rule. L'Hopital's rule says let's take the derivative of the numerator, so that's 1/2 x to the negative 1/2. The derivative of the denominator, e to the x. Let's clean this up. So limit as x approaches infinity, and this is a 1 in the numerator and a 2x to the 1/2 e to the x. Now from here, I'm just going to now try to direct substitute infinity. So I have 1 in the numerator. I have 2 times, what do I get here? X to the 1/2. So as x gets bigger and bigger, that gets bigger and bigger. And as e to the x, x gets bigger and bigger, that gets bigger and bigger. So this is really 1 divided by infinity, right? And so if I get 1 divided by infinity, that limit is 0. So we have 0 twice. Now let's look at that last one. For the last one, can I do direct substitution? No. But do I have to use L'Hopital? No. So in this one, if I wasn't asked directly to use L'Hopital's rule, I would simplify this to x plus 4, x minus 4 in the denominator. And that would give me the limit as x approaches 4 of 3 divided by x plus 4. And now I can do direct substitution. So that's 3 divided by 4 plus 4, or 3/8. Now I do want to point out to you that sometimes I will ask you to evaluate a limit in 2 different ways. So once using an algebraic technique and once using L'Hopital's rule. So just for good practice, let's use L'Hopital's rule on this one as well. L'Hopital's rule says take the derivative of the numerator. So I would think about this numerator as 3x minus 12. So the derivative is 3. And the derivative of the denominator would be 2x. And then minus 16 would be 0. So it's just 3 over 2x. So now I can use direct substitution. 3 divided by 2 times 4, which is 3 divided by 8. So we can see that I get the same limit whether I use L'Hopital's rule or an algebraic technique. Here are 2 questions for you to try on your own, so try them both. When you're done, press play to see how you did. So notice it says you can use L'Hopital's, but you don't have to. So if I'm looking at my first fraction, my rational function, I can see that I have both a rational function and a radical in my denominator. So this expression on the bottom is x squared plus 1 to the 1/2 and x in the numerator. And that's not going to be fun to find the derivative of because now we're talking about chain rule. So typically what you're going to do on a question like this is you're going to look for the greatest degree of x. So here x is to the first degree. This is the squared, but it's the square root of a squared, so that's actually x to the first also. So what I'm going to do is I'm going to rewrite this as the limit as x approaches infinity, and I'm going to take everything divided by x. Now keep in mind, x might look like x, or it might look like the square root of x squared, which is the same thing. So inside my radical, I've got x squared and then plus 1, and because I'm inside my radical, I'm dividing by the square root of x squared. So I don't have to show the square root again because it's already here. And this tells me that I have the limit as x approaches infinity, x divided by the square root of x squared, which we said is x, so x divided by x is 1 in the numerator. In the denominator, x squared divided by x squared gives me 1, and then I have 1 divided by x squared. So what's going to happen as I not direct substitute, because you can't directly substitute infinity, but I can reason through this. What's going to happen? My numerator is obviously going to be 1. And what's happening in the denominator? I have 1 plus this value is going to get very, very big because we're going to infinity. So it's 1 plus 1 divided by 0. So the square root of 1, which is 1. So my limit here is actually just 1. And I didn't have to use L'Hopital's. Let's look at the second question. For the second question, again, if I try direct substitution, it's not going to work right away. But this one I am going to use L'Hopital's. So I'm going to take the limit as x approaches infinity, and I can say the derivative with respect to x of e to the x minus 1, and then the derivative with respect to x of 1 minus x cubed. And that's going to give me, again, keep writing that limit until we find the limit. The derivative of e to the x, as we know, is e to the x. The derivative of minus 1 is 0. The derivative on the denominator, 1 is 0, and then minus x cubed gives me negative 3x squared. I haven't solved anything though, so I still can't find the limit because I would still get infinity over infinity. So now let's continue. I'm going to go ahead and take the derivative again for the sake of space and time. I'm not going to rewrite the d dx. I'm just going to cheat and write it like this. So what's the derivative of e to the x? Oh, still e to the x. What's the derivative of negative 3x squared? It's negative 6x. Am I where I need to be? Not quite. Let's go one more time with L'Hopital. And I get the derivative of e to the x is e to the x, and the derivative of negative 6x is negative 6. And now, finally, I can say, let's evaluate. So we know that the numerator is going to approach infinity, and the denominator is going to be negative 6, so that gives me a negative infinity. And I encourage you to graph one or both of those functions to determine or to verify our results. Coming up next, we're going to review inverse trigonometric functions.